Welcome to the session 5 of week 2 in digital signal processing. Let us continue with the properties of DFT. Let us go for the next property, that is symmetry property of DFT. Let us assume the sequence, discrete sequence x of n and its DFT both are complex value. The sequences can be written or can be expressed as x of n equal to xr of n plus j xi of n, where n runs from 0 to capital N minus 1. So here this x of n is the discrete sequence. This x sub r of n is nothing but the real part of x of n, and this x sub I of n is nothing but the imaginary part of x of n. Similarly, I can consider its DFT also, DFT x of k with its real part xr of k and with its imaginary part xi of k. So this is what is the uh, inputs for this property, that is I have considered the discrete time sequence and DFT both are in complex version, that is x of n is equal to xr of n plus j xi of n, and x of k is equal to xr of k plus j xi of k. So let us substitute the basic equation of DFT inside this first equation, that is 26.1. So let us write the basic equation of DFT first. So how can you write is, let us write it as x of k is equal to x of k is equal to summation x of n e raised to minus a 2 pi k small n upon capital N. N runs from 0 to n minus 1. If we substitute this value of x of n in this expression, what I can write further, let me use some different pen. So what I can write is x of k summation n runs from 0 to n minus 1. Instead of x of n, I can write this complete x sub r of n x sub r of n plus j x sub I of n. So this is my complete x of n I have written into e raised to minus j 2 pi k upon capital N. So now this e raised to minus j 2 pi k n upon capital N, that we can write in the Euler's form, and I can write it as, let's write it here. Yes, here we can write as x of k is equal to summation n runs from 0 to n minus 1 x r of n plus j xi of n multiplied by this e raised to minus j 2 pi k n by capital N. I can write in terms of cosine and sine. So cosine of 2 pi kn by capital N minus j sine of 2 pi kn by capital N, and I can complete the bracket. I can complete the bracket. So this what is the equation which I'm getting now. Now if I want to find out the real part, so what is the real part now? Real part is what? XR of k. So if I want to find out the real part, how can I find it? Is, let us use some, if I want the real part, so this XR of n, if I multiply it with this cos, then I'll get the real part. So this is the first term. And if I see here this j and this j, so j multiplied by j would be equal to j square. J square is minus 1. Along with this minus 1, it will become plus 1. So this xi of n and this sign will also contribute to real part. So this real part, I got it by comparing this expression. So I got the real part here. Then we can go for the imaginary part also. So we can see here, if I want the imaginary part, what I should do. Let me clear all the, let me use some another pen. If I want the imaginary part, then this xr of n, let us use another notation, and this sign. So this multiplied with this, I will get the one part of imaginary part of DFT, and another part cosine and xi of n. Let us use double circle here. So if I use this, I will get the second part of imaginary term of DFT. So like this. So this is what we have done it by considering only the first, that is 26.1. If I do the same exercise by considering 26.2, I can get the real part of, I can get the inverse DFT, inverse DFT expressions. Let me clear all this. So here I'm getting, if I'm considering this expression, I'm getting the expressions for the DFT. If I go for this expression, if I carry out the same exercise, then I will have the IDFT expressions. I will get the IDFT expressions. Okay. So let us move further now. So let's consider my x of n is a real valued sequence. If it is a real valued sequence, then what I can have is x of n minus k is equal to x of minus k is equal to x asterisk of k. Here also you have to consider the basic definition of DFT, like what you can write is x of k is equal to the same expression. You can write it one more time. There is x of n e raised to minus j 2 pi k n by capital N, n runs from 0 to n minus 1. Okay, now we can again go for the next. You can put k equal to n minus k. You can elaborate it. So minus j 2 pi k would be replaced with n minus n, n upon capital N. and runs from 0 to n minus 1. We can split this bracket, and after splitting this bracket, whatever I'm getting is x of minus k. Ultimately, it is equal to complex conjugate of x of k, and that is what is written here. Okay, so that what is the symmetry property. If my x of n is real value, then obviously my x of uh, minus k would be equal to x of capital N minus k. So let us go towards the next part, that is if my x of n is real and even. So for this, for understanding this, just now we have written one expression, just we'll write it one more time for the quick reference. Write it as x of k is equal to summation randoms from 0 to n minus 1 x r of n plus j x I of n, and then cosine of 2 pi k n by capital N minus j sine of, let me complete this bracket, 2 pi k n by capital N. So this expression we have to use for this, and this we have derived just now when we are doing the exercise for this and for this. You can go back in the video and you can check this expression. So I have to use this expression now. Now my signal is real and even. Okay, so if my signal is real and even, just we have seen in the previous session that x of n is equal to x of capital N minus n. If it is real and even, then uh, how should be my x of k? So x of k should be real and even. So if it is to be real and even, so if I want it to be real, so this part I have to consider, and I have to consider this is to be the even part. X of n into cos, it would be real as well as even, but if I modify this x of n into the sign is odd, again this say is odd part, you have to do the multiplication. So this x of n into cos, this will give me the even and real signal. So x of k to x of k is equal to summation x of n cosine of 2 pi k n upon capital N. So if I will get this DFT, so I can find out from this equation I can find out the IDFT also. So it is the reverse of this, that is x of n is equal to 1 by n summation x of k cos 2 pi k n upon capital N. So this is what is for the if x of n is real and even. Let us move further. Yeah, this I have brought it for the quick reference. Let us erase this. This equation will keep it as it is for our reference. The next part is x of n is to be real and odd. So for x of n to be real and odd, what we know is the x of n is equal to minus x of capital N minus n. If I want it to be real and odd, means what I should have is, you can see this XOR of n into sine, because XOR of n, sorry, XOR of n into sine. So this is the case into sine, because what I want is the real and odd nature. Okay, so I don't want even part, so this will not come over there. We'll multiply it. So what I'm getting is this x of k is equal to minus j summation x of n into sine of 2 pi kn upon capital N. Okay. Similarly, if I have this the equation as a DFT, I can find out its IDFT. So if I find this IDFT, x of n will come here, and I will get this as an equation for the IDFT. Let's go further. If whenever the for the next case, that is the when x of n is purely imaginary. Okay, so this is the case 4. This is the case 4, and we have removed that expression. I think we need to write it one more time. X of k is equal to, what I can write is summation and runs from 0 to n minus 1 x of n plus xi of n multiplied by cosine of 2 pi kn upon n minus j sine of 2 pi kn upon n. Now what I want is, or what I have here is the purely imaginary terms, that is x of n is equal to j I n. So j I n, I have this term, so I can multiply this with cos, and I can multiply the same term with the sine. So I can have the real part when I will multiply this xi of n with sine. So this j and j will be j square with minus sign. So minus minus becomes plus. So I will get here xi of n into sine 2 pi kn by n as a real term. And for the imaginary term, I will have xi of n into cosine with the j sine. With the not j sine, xi of n into cosine term. Okay, so that's what is the case of DFT when my x of n is purely imaginary. Let us go further for the next property, that is circular convolution property, very important property, multiplication of two DFTs and circular convolution. So yeah, what this property tells me is that multiplication of two DFTs, multiplication of two DFT is equivalent to the circular convolution of their sequences. Okay, so let us go further. Let us first write the statement for the circular convolution. If my x1 of n has its endpoint DFT as x1 of k, and if x2 of n has its endpoint DFT as x2 of k, then circular convolution of x1 of n and x2 of n will be equal to multiplication of x1 of k and x2 of k. So let us go further. Let's start with the input. So let us consider the two finite duration sequences x1 of n and x2 of n of length of every of individual length capital N. So the respective DFT equations, I can write it as x1 of n is equal to summation x1 of n. Sorry, x1 of k is equal to summation x1 of n e raised to minus j 2 pi kn upon capital N, k runs from 0 to n minus 1. And similarly, I can write down the expression for the second DFT, that is x2 of k. So x2 of k is equal to summation x2 of n e raised to minus j 2 pi kn upon capital N, k runs from 0 to n minus 1. Now once I got these two, Now let us denote the multiplication of two DFTs, that is multiplication of two DFTs, that is x1 of k into x2 of k as x3 of k. Let us denote this multiplication as x3 of k. Okay. So just after multiplying this, what I can write is x3 of k equal to x1 of k into x2 of k. If I do its inverse uh, uh, DFT, then x3 of k, inverse DFT of x3 of k, I can write it as x3 of m is equal to summation 1 upon n summation x3 of k raised to j2 pi k m upon capital N. Okay. So once I got this, now this x3 of k, I know that this x3 of k is equal to x0 of k into x2 of k. So I will just replace this x3 of k with x1 of k into x2 of k. You can put this value of x of k from this expression, and I will put this value of x2 of k from this expression. So I will put these values, and I will get the, so this is my x1 of k. Just 1 second. This is my x1 of k, and this is my x2 of k. You change the variable here from n to l for just uh, differentiation. We have used here dummy variable. Now we can change the summation orders. So we can change the summation orders in the fashion 1 upon n will remain as it is. So I can bring this summation n runs from 0 to n minus 1 of x of n. I can write it here. Then summation l runs from 0 to n minus 1 x2 of l. I can write it here, and whatever the remaining terms are there, this summation I can write it here, and these exponents 1, 2, 3. So all these three exponents I can write it here. You can see here it is minus n, it is minus l, and it is m. So I can write it as m minus n minus l. So once I understood this, we'll go further. We'll bring these equations in the next slide for our quick reference. At till this point. Now let us assume that this a, for elaborating this, let us assume one substitution, that is a equal to e raised to j2 pi m minus n minus l upon n, which accept this k. Except this k, everything is included in a. So if I consider only this curly bracket, so what I can write is it is summation k runs from 0 to n minus 1, and it is now a raised to k. So I have written here as summation k runs from 0 to n minus 1. I have written as it is. This substitution I can put here, this a, and what is the remaining term is the k, so we can write it as a raised to k. Now if you see this particular substitution, then if I put here a equal to 1, if I put here a equal to 1, so it becomes 1 raised to k. 1 raised to k means 1 raised to anything would be 1. So this is ultimately 1. And how many times I have to add it? I have to add it from 0 to n minus 1 time, means I have to add 1 for capital N times. So ultimately the summation would be n only. So if I put a equal to 1 here, if my a is equal to 1, this summation is going to be equal to capital N. And when this A is going to be equal to 1, this A would be going to be, is going to be equal to 1 when my M minus N minus L is multiples of capital N. Once I can write here, M minus N minus L is multiples of N. So I can write it plus Pn or minus Pn, doesn't matter. P is integer, I can write it here. So ultimately what I can write, for if I want to write in terms of the L, so L will come towards the right hand side, it will go towards the left hand side. So it becomes N minus L plus Pn. So this we have to remember for next few seconds. So this is the case, this is the value when my A is equal to 1. Now if my A is not equal to 1, if my A is not equal to 1, so I have to use my usual formula 1 minus A raised to N upon 1 minus A. Okay, so like this. A raised to lower limit, that is A raised to 0, that is 1. A raised to upper limit plus 1, so it is N minus 1, so N minus 1 plus 1, it will become A raised to N upon 1 minus A. If we'll put this value of A here, so what I'll get is 1 minus this value of A raised to N. Now this N and this N will get cancelled. So what remains is 1 minus e raised to j 2 pi. And this M minus L minus N is nothing but what? All are the constants. So this should be the constant time of 2 pi. So ultimately this e raised to term will become 1. So if this is 1, so 1 minus 1, it would be 0. So what I can conclude is, if my A equal to 1, means if my M minus L minus N is multiple of capital N, ultimately L equal to M minus N plus Pn, that is written here, and that is M minus N point, that is capital N. Okay, so if A is equal to 1, I will get capital N. If A is not equal to 1, I will get 0. So this is my ultimate conclusion from this calculation. So I can put this value in this expression, and I can go further now. So from this 29.2 is from this expression, sorry, from this 29.2 and 28.5. So what I can write is a summation A raised to k. So this is summation A raised to k. And instead of this, what I'm going to write is capital N. So this is complete. And if I'm going to write it capital N, so it is in the numerator. So this N and this N will get cancelled. And this L is nothing but what? L is nothing but M minus N Pn. So this ultimately I can write it as M minus N subscript capital N. So all these substitutions will do, we'll put it in the equation. So it is N, this both N will get cancelled. What I got is M minus N plus Pn. Let us move towards the next slide. Okay, let us bring these equations in the further slides for our reference. Okay, so we will till this point. This one. Now what is this? This x1 of n and x2 of m minus n, capital N, is nothing but what? Is nothing but the circular convolution of x1 of n and x2 of n. So this circular convolution of x1 of n and x2 of n is nothing but what? x3 of m, and its DFT is what? x3 of k. x3 of m, its DFT is x3 of k, and x3 of k is equal to x1 of k into x2 of k. So So ultimately, we have proved it that circular convolution of x of n x2 of n is nothing but x3 of m, and this x3 of m its DFT is x3 of k, and it is equal to x1 of k and x2 of k. So we can write that circular convolution of x1 of k, its endpoint DFT is x1 of k into x2 of k. So what can conclude is multiplication of two DFTs, multiplication of two DFTs. So these are the two DFTs, x1 of k and x2 of k, is equivalent to circular convolution of their time domain sequences, and that is what is the circular convolution.